In this video tutorial, we will continue our discussion of the solubility product by looking at the common ion effect, as well as predicting the formation of precipitates. Now, if you recall, KSP is the equilibrium constant that describes how well a particular substance will dissolve. By expressing it as a ratio of dissolved over undissolved, just looking at the KSP value is enough to tell you whether a substance is soluble or insoluble. Now, in previous years, you may have been given a solubility chart, like this one over here, or a set of solubility rules to determine whether a compound is soluble in water or not soluble in water. So for instance, if I had asked you, is silver chloride soluble or insoluble, you would have just taken a look at the chart and said, okay, here's silver, here's chlorine. When I go through them, it says I for insoluble, and that is how you would determine whether a compound was soluble or insoluble in water. This year, however, you'll be given a set of KSP values in this table, for instance, over here. So silver chloride, instead of using a chart, you would just look it up over here. Silver chloride, 1.6 times 10 to the power negative 10. And because that's a very, very small number, that means that the denominator is a very large number. And that tells me there's a lot more undissolved component than there is dissolved component. And that shows me that the silver chloride is likely to be insoluble in water. Now, up until this point, we've been dealing with examples where a compound is being dissolved in pure water. But what happens if we try to dissolve that same compound in a sample that is not pure water? For example, we all know salt dissolves quite well in pure water, about 36 grams per 100 mils of water at around 20 degrees Celsius. But what if I already had a beaker that had 10 grams of salt already inside of it? Would I still be able to dissolve the full 36 grams? No, I'd only have room for 26 grams at that point. And so by having some salt already pre-dissolved in solution, I can't dissolve as much as I could have if it had been just pure water instead. The same holds true even if they're not the exact same compound, so long as they contain a common ion between them. Let's take a look at an example to understand why this is. So over here, what is the molar solubility of silver bromide in pure water? Since we're looking at molar solubility, you don't need an ice chart. By definition, molar solubility is how much can it dissolve at equilibrium. All right, so just at equilibrium, how much silver bromide will actually break apart? So for every one silver bromide that breaks apart, one silver is released and one bromine ion is released because it's a 1:1:1 ratio. All right. So let X represent the amount of silver released, and since it's a 1:1 ratio, that's also the same value for bromine. All right. So punch it into your equilibrium expression. Don't forget that silver bromide is not factored in because it is a pure solid. So it's just the products, the solubility products over here, silver and bromine, X squared, and we can find the KSP value from our reference chart. In which case it's 6.5 times 10 to the power negative 13. Solve for X, and we get 8.06 times 10 to the power negative 7 moles per liter, meaning 8.06 times 10 to the power negative 7 moles of silver bromide can dissolve in 1 liter of solution as long as it's in pure water. But what happens in part B if the solution is not pure? What if there's already some potassium bromide in solution? Now, potassium bromide is quite soluble in water. We can tell this because when we look at our reference sheet, check under the KSP chart, you will see that in the bromide section, potassium bromide is not listed. We typically only list compounds that are insoluble in water, those with a low KSP value. Like KSP value for potassium bromide, it's around 20. Versus all these other ones, they're in the 10 to the power negative 29 range, negative 13, negative 22. These guys are insoluble, and so if you don't find it on the chart, you may assume that the compound is soluble instead with a large KSP value. And because the KSP value is large, it's not really needed in our calculations, at least for this course anyway, so we leave it out. So because potassium bromide is very soluble in water, there's no need for you to write down equilibrium arrow. Just draw a one-headed arrow to show that it completely breaks up, completely dissolves and dissociates. So one potassium bromide will release one potassium ion and one bromine ion. However, if you look back in our question, it says it's a 0.20 molar solution of KBr. So if it's a 0.2 molar solution of KBr, meaning 0.2 moles of potassium bromide dissolved in 1 liter of solution, then that means the concentration of potassium and bromine are 0.2 moles per liter and 0.2 moles per liter as well, because it's a 1:1:1 ratio. So when the question asks how much silver bromide can dissolve in the solution contains 0.20 moles of potassium bromide, what we're trying to say is that there's already some bromine ions floating around our solution. When we try to dump in silver bromide into the solution, silver will be released, bromine will also be released, but there is already some bromine in the solution ahead of time. So how does this scenario compare with this scenario where it's just pure water? Look at the calculations then. Because the pure water had no bromine concentration initially, it's just an X value. But with bromine, there was already a head start from the potassium bromide of 0.2. Take a look at what happens when we put that in our calculations. Instead of X squared, we now have X and X plus 0.2. Now, you could use the quadratic equation. My recommendation is use the approximation rule instead. But once you solve for this value, X comes out to be 3.25 times 10 to the power negative 11 moles per liter. Look at that. Compare this molar solubility in potassium bromide solution, one that already has a common ion inside of it, versus the solubility in pure water instead. All right? It's over 25,000 times more soluble if there was no bromine head start than if there was a bromine common ion floating around prior to you trying to dissolve it. And this is the common ion effect. Essentially, your ability to dissolve, your solubility, is greatly decreased if there is a common ion already floating around in solution. That common ion prevents you from breaking up or dissolving as much as you could have because there's already something there. Now, some students will ask, what about the potassium? Why don't we include it in any of this? Potassium is what we refer to as a spectator ion, because it does not participate in the solubility equilibrium. It doesn't prevent the silver bromide from dissolving, nor does it improve its chances of dissolving either. And so the only common ion we have between the potassium bromide and the silver bromide is the bromine ion, and only the bromine ion will cause interference in the dissolution or the solubility of the silver bromide. Alright, let's try out a sample question. You will of course require the use of your reference sheet, specifically that of the KSP values located in the table over here. You can find all of this on our Google Classroom. Now, what I want you to do is press pause, try out this question. When you're ready, unpause the video and we'll go over the solution together. Alright, so the question asks, how many grams of silver iodide can dissolve in a 0.725 liter solution of 0.440 mole per liter magnesium iodide? So essentially, what we're doing over here is we are dissolving magnesium iodide into our solution and trying to dissolve silver iodide at the same time. So when we check our solubility reference sheet, under iodide, I only see silver iodide, I don't see magnesium iodide, showing that the magnesium iodide will be soluble while the silver iodide will form a solubility equilibrium that we have to take into consideration. So if we have 0.440 moles per liter of magnesium iodide and all of it breaks up, all of it dissolves because it's very soluble, that means I'll have 0.440 moles per liter of magnesium, but 0.880 moles per liter of iodine, because for every one magnesium iodide, 2 iodine ions are released. So we got to double this amount over here. This of course results in the common ion effect because now we have a common ion, the iodine ion, between these two compounds. And so the magnesium iodide will interfere with the silver iodide's ability to break up and dissolve into solution because there's already iodines floating around in solution. So the first thing we'll do is to write out the expression or the equation showing how silver iodide will dissolve in water. It'll go from a solid to break up into silver ions and an iodine ion in a 1:1:1 ratio. From there, let X represent the amount of silver that's released. Now, because silver starts off with 0, we can just write down X. However, iodine starts off with 0.880 moles per liter, courtesy of the magnesium iodide that was already in the solution. So because the iodine already had a head start, that's our common ion. We're going to write down X plus 0.880 instead. From there, we can substitute our values into the KSP expression. Remember that we don't need to factor in the silver iodide because it's a pure solid. And then we solve for X. You could use the quadratic equation, but my recommendation is to use the approximation rule instead. As a quick reminder, how do we use it? The 0.880, take the initial concentration, divide it by KSP, 1.5 10 to the power negative 16. And if this value is greater than or equal to 1,000, that means the X value is at least 3 orders of magnitude smaller than 0.880. So it's negligible in comparison. And so we can assume that the X value over here is a 0. So once we punch it in, we do see that the value is much greater than 1,000. X is negligible. I can simplify this expression into this one over here. And this makes it a lot easier to do our calculations. And when we've done so, X is equal to 1.70 times 10 to the power negative 16 moles per liter. Because for every 1 silver iodide that breaks up, 1 silver is released. Therefore, its X value over here is the same value over here. So that means that 1.70 times 10 to the power negative 16 moles of silver iodide can dissolve in a 1 liter solution. Since the volume, however, is 0.725 liters, not 1 liter, as we said over here, we need to find out how many moles of silver iodide was dissolved. So take the concentration, multiply it by the volume, and you're left with the moles. 1.23 times 10 to the power negative 16 moles of silver iodide can dissolve. But the question asked how many grams of silver iodide can dissolve. So then we got to convert it from a mass into a mass, which is equal to moles times the molar mass. You got the mole value here. Molar mass value can be found from the periodic table. And there you have it, 2.89 times 10 to the power negative 14 grams of silver iodide can dissolve if you had a solution that was 0.440 moles per liter of magnesium iodide already dissolved in that solution. Alright, so now that we have an understanding of the common ion effect, we can start to predict whether a precipitate will actually form. So if you recall, a precipitate is an insoluble product that forms from a reaction between two soluble ionic compounds. Alright, now back in grade 10 and grade 11, you would just use the solubility chart or solubility table and to determine whether a precipitate will form. But remember, just because something is considered to be insoluble doesn't mean it doesn't dissolve, it just means very little of it dissolves. So if there's very little of it in the first place, then you might not actually make a precipitate. It may still dissolve completely in the solution if it's a small enough quantity. And that's why we have to factor in, or rather take into consideration, the KSP values over here. And so by comparing the QSP value, the current concentration of ions in our solution, to the KSP value, what's allowed to be in the solution, we can determine whether or not a precipitate will form. All right? So KSP tells us how much we're allowed to have in our solution dissolved, whereas QSP tells us how much we have currently in our solution. So if the QSP, how much we have, is less than KSP, how much we're allowed to have, then there will be no precipitate. That means I can still dissolve more if I needed to. Versus if the QSP, how much I have, is greater than the KSP, how much I'm allowed, that tells me I've dissolved more than I'm allowed to have, and so there will be excess sitting around as a solid instead, otherwise known as a precipitate. So let's take a look at a sample question over here. 1 milliliter of 0.1 molar silver nitrate is added to 1 liter of 0.001 molar potassium chloride. Will a precipitate form? So the first step is to write out the chemical equation for this. Silver nitrate reacts with potassium chloride. This is a double displacement reaction, so we can predict what's going to happen on the other side. Silver chloride and potassium nitrate will be formed. Next up, we need to identify which of these is most likely to be my precipitate, the silver chloride or the potassium nitrate. So I'm going to consult my KSP table, and there I see that silver chloride is present, so that means it's insoluble, most likely to form a precipitate, whereas potassium nitrate is nowhere on this table. In fact, there are no nitrates on this table because generally nitrates are extremely soluble. So that means silver chloride is going to be my precipitate. That's the one I need to focus on. Now I've just noticed that my KSP value is slightly different than the one we have here on our sheet. 1.6 times 10 to the power negative 10 versus 1.8 times 10 to the power negative 10. So depending on the source that you use, different textbooks will have slightly different values. Just make sure that their magnitudes are in the same area. This value over here will differ depending on what your source is, which textbook you're using. However, on a test, I will be using the values from here instead, the ones that I provide you. But because I've already written down the answers, I'm just going to continue on using this one that I found on Google. Just be aware that's why there's a slight difference between this KSP value versus this KSP value over here. I did the same error over here. I used Google instead of using this sheet. But please remember, on a test, I will be using values from this sheet specifically, not the ones from Google. All right. So silver chloride is going to be our precipitate. That means when I dump it in water, it will break up into one silver ion and one chlorine ion. that means its QSP expression will look like this. So what I want to do, the overall game plan, is to find out what is the silver concentration in my solution, so I can punch it in here. What is the chlorine concentration in this solution, so I can punch it in here. Calculate QSP. Once I calculate QSP, compare it to the KSP value to see whether or not I've overshot what I'm allowed to have, or do I have any more room left in my solution. So if QSP is less than KSP, no precipitate will form. If QSP is greater than KSP, I've added too much, there will be a precipitate form. Now, because we're adding two solutions together, the initial concentrations we have, 0.1 molar and 0.001 molar, they're not going to be exactly the same anymore. So what I mean is, I've dumped in 0.001 liters of silver nitrate, and I've dumped in 1 liter of potassium chloride. That means the new volume together, they make a new solution, and this new solution volume is 1.001 liters. That has to be factored in. Because of the new solution volume, that affects my concentrations. They have changed now. So the silver nitrate concentration is no longer 0.1 molar, and the potassium chloride concentration is no longer 0.001 molar either. All right. So what we're going to do is we're going to recalculate concentrations. Mole divided by the new volume. To calculate moles, moles is equal to C times the V, the old concentration, times the old volume. That'll tell you how many moles of silver nitrate there were originally. Divide by the new volume, and now we've got the new concentration of silver nitrate. We'll do the same with the potassium chloride. There's our new volume, 1 liter plus the 0.001. And the old moles was C, concentration, times V. And we get the old number of moles divided by the new volume, gives me the new concentration. Now, I don't care about the silver nitrate. I don't care about the potassium chloride. What I do care about is the silver chloride. That's my precipitate. So I really only care about the silver ions and the chlorine ions. Thankfully, this was all a 1-to-1 ratio. Silver versus silver nitrate. For every 1 silver nitrate, it releases 1 silver. So that means the silver concentration and the silver nitrate concentration are identical. Same thing with the potassium chloride. For every 1 KCl that breaks up, 1 Cl is released. It's a 1-to-1 ratio. So therefore the KCl concentration is the chlorine concentration. This won't always be the case. It may not always be a 1-to-1 ratio. It may be a 1-to-2 or 2-to-3. Just make sure you pay attention and watch carefully what the subscripts are. So moving on to step 4, now that we have the concentration of the silver ion and the chlorine ion, we can punch that into our calculation. Silver concentration, chlorine concentration, multiply them together, we get the QSP. We compare our QSP of 1 times 10 to the power negative 7 versus the KSP of 1.8 times 10 to the power negative 10, and we see, oh look, we've got more silver and chlorine dissolved in solution than I'm allowed to have. I should only have this much, but instead I put in this much. So that means that the ion concentration has exceeded its solubility. I put too much inside, not enough water to dissolve it all, and so there will be a solid component sitting at the bottom, undissolved, and we call that our precipitate. And so therefore a precipitate will form in this solution if I mix these two together in these quantities and in these concentrations. So these types of questions are pretty standard. You'll definitely find them on the test, on the exam, and you'll probably even see them on first year university as well. So make sure you are good to go with these types of questions. They aren't difficult, but they can be long and tedious. Just make sure that you remember to add the 2 volumes up. That's a very common mistake students make. Make sure that the ratio is proper. It won't always be 1-to-1. That's another common mistake. But other than that, just compare QSP to your KSP to see whether or not a precipitate will form, and that's pretty much it. Alright, so here's another sample question. Once again, press pause, try it out yourself. When you're ready, press play, and we'll go over the solution together. Alright, so 375 milliliters of 2.55 times 10 to the power negative 3 mole per liter lead 2 nitrate is added to 125 milliliters of 6.15 times 10 to the power negative 4 moles per liter potassium iodide. Will a precipitate form? So the first step we're going to do is to write out the chemical equation. Lead 2 nitrate, potassium iodide. This is a double displacement reaction, so we're going to follow the pattern and we get potassium nitrate and lead 2 iodide being formed. Don't forget to balance your equation as well. Next, we need to identify which of these 2 products is going to be our precipitate. For that, we have to go back to our reference sheet and look up their KSP values. Potassium nitrate is not included here. As you can see, most nitrates are going to be soluble, so they're not included in the KSP charts. We only include insoluble compounds on our KSP tables. However, lead 2 iodide is present, and it's got a KSP value of 1.4 times 10 to the power negative 8, telling us that's not very soluble at all. Thus, lead 2 iodide is most likely to be our precipitate. So we can then write out the dissolution equation for lead 2 iodide, and when it dissolves, it breaks up for every 1 lead 2 iodide into 1 lead 2 plus ion, and it releases 2 iodine ions. It's very important that you write it as 2 iodines and not as I2, because this coefficient needs to be factored in to the QSP exponent. Now, calculating QSP is products over reactants, or in this case, dissolved over the undissolved. But again, we ignore the undissolved component because it's a pure solid. So lead 2 plus concentration measured in moles per liter, the iodine concentration measured in moles per liter, and of course the coefficient of a 2 becomes a squared. Now it's very important that you don't write down 2I on the inside. We just want the iodine concentration, not double the iodine concentration. Doubling over here is already factored in with the exponent. You don't need to double it again, otherwise you will get the wrong answer. Once we have solved for QSP, we can then compare it to KSP. So remember, QSP tells you what are the concentration of the ions right now, while KSP tells you what are the concentration of the ions supposed to be. All right, how much are you allowed to have? So if QSP is less than KSP, that means I haven't dissolved up to the maximum. I still have room, so therefore no precipitate will form. However, if QSP is larger than KSP, so that means I have more than what is allowed, then yes, you will have excess precipitate sitting on the bottom of your beaker. Alright, so that is a general overview for the entire question. Let's go on and do some calculations. So over here we've got lead 2 nitrate, 2.55 10 to the power negative 3 molar, and we're going to pour 375 milliliters of it into my beaker. To this we're going to add some potassium iodide, and this potassium iodide is 6.15 times 10 to the power negative 4 molar, and we are going to dump 125 mils of this into the solution. So because we're combining the two volumes together, we're going to have a new total volume. If you have a new total volume, then of course your old concentrations are no longer true. They're going to be more dilute at this point. So we need to factor that in and identify what is the new concentration for each of these compounds now that we have a new volume. For that, mole is equal to C times V. Find out how many moles of lead nitrate were originally placed inside this beaker. So there's a concentration, there's the volume. Don't forget to convert to liters. A lot of students forget that milliliters must be converted to liters because molarity, or molar concentration, is measured in moles per liter. All right? That gives us 9.56 times 10 to the power negative 4 moles of lead 2 nitrate. Let's do the same thing on the potassium iodide side. Here was the original concentration. I want to know how many moles did I throw into this beaker. Moles equal to C times V, concentration times volume. There it is. Again, I convert to liters, and I get 7.68 times 10 to the power negative 5 moles of potassium iodide. Now remember, when we're calculating QSP, we don't care about the lead nitrate. We do care about the lead component, though. So that's what we're going to do. We're going to try to find out how many moles of lead there are. For every 1 lead nitrate that breaks up, 1 lead is released. So therefore, it's a 1-to-1 ratio. Thus, if you have this many moles of lead 2 nitrate, then you have the same number of moles of lead 2 plus itself. Same thing on the other side with the potassium iodide. Again, I don't need the whole potassium iodide. I just want the iodine component. So what we're going to do is we're going to find out how many moles of iodine are floating around solution. Again, for every 1 potassium iodide that breaks up, 1 iodine is released. Thus, it's a 1-to-1 ratio. So if this is how many moles of potassium iodide I have, 1-to-1 ratio, this is how many moles of iodine ions I have as well. But again, we can't use moles. We have to use moles per liter when we punch it into our QSP expression. So now that we know the moles of lead 2 plus, we can calculate the new concentration of lead 2 plus. Mole divided by volume. The new volume is 0.500 liters. Don't forget to convert from milliliters to liters. There's the mole value, and this is the concentration of lead 2 plus by itself. Do the same thing for the iodine on this side over here. And again, it is a 1-to-1 ratio. For every 1 potassium iodide that's broken up, 1 iodine is released. So therefore, we have 7.68 times 10 to the power negative 5 moles of iodine divided over a new solution volume of 500 mils, or 0.500 liters. And that gives me a new concentration of 1.54 times 10 to the power negative 4 moles per liter iodine. We can now write out our QSP expression, lead 2 plus ion concentration times the iodine ion concentration squared, and substitute the values in, and we solve and get QSP, 4.53 times 10 to the power negative 11. We then compare to the KSP value, and if you recall, KSP for lead 2 iodide is 1.4 times 10 to the power negative 8, and we see that KSP is larger than QSP. So remember, KSP tells me how much I'm allowed to dissolve in solution. QSP tells me how much I currently have dissolved in solution. So because my maximum is greater than what I currently have, I can still add more lead 2 iodide into solution and it will still dissolve. Thus, no precipitate will form.